Hello, and we are using TensorFlow, a popular open source machine learning framework. And here, TensorFlow's Craze AIP helps us define and build a neural network easily. And we will start by creating a sequential neural network where each layer fits directly into the next, forming a simple, straightforward model agriculture and setting a random seed. In the first line in this code block, we use the tf.random.set seed 1, 2, 3, 4 in block set. Setting a random seed ensures that our models initial weights and other random processes produce the same result every time we run the code. This is especially useful for debugging and testing changes as it brings to models performance. By specifying 1, 2, 3, 4 as our seed, TensorFlow will use this number to initialize randomness in a way that makes result representable. Without setting a seed, results will vary with each run, making a completion harder. In our second context, creating a sequential model, we define the model as sequential, which is a class for stacking layers in sequence. This means that each layer's output becomes the next layer's input. Using sequential is ideal for simpler layer by layer models without branching paths or multiple input or outputs. In the code, we name the model is my model, which is a good habit to follow, especially when working with complex architectures or multiple models. And our third context is creating a sequential model, and we define the model as sequential, which is a class for stacking layers in sequence. This means that each layer's output becomes the next layer's input. Using sequential is ideal for simple layer by layer models without branching paths or multiple inputs. Our first layer is a dense layer with 55 units, which means it contains the 25 neurons. The input shape tells the model to expect input vectors with 400 features. You could think of these features as individual pieces of data about each input. This layer uses the ReLU activation functions. ReLU, which stands to rectified linear units, is one of the most common activations. It introduces non-linearity to help the model learn complex relationships and handle large datasets. ReLU outputs the input directly if it's positive, otherwise it outputs 0, which help prevent issues like exploding gradients. For softmax function, a multi-class neural network generates an output. One output is selected as predicted answers. In the output layer, a vector z is generated by linear function, which is fed into a softmax function. The softmax function converts z into probability distribution as described below. After the applying softmax, each output will be between 0 and 1, and output will sum to 1. They can interpreted as probabilities. The larger inputs to the softmax will correspond to larger outputs probabilities. I'm starting this code block, and all test we saw the all test passed sentences. In terms of parameters, these layers 10,055 parameters. Parameters in a dense layer are calculated as the number of input features times the number of neurons in a layer plus the biases. In our case, this is 10,025 parameters include both weights, connection between the input and the neurons, and biases. And second layer, adding another dense layer. Second layer is also dense layer but with 15 units, meaning it has 15 neurons. Each neuron in this layer is fully connected to all neurons in the previous layer. We again use the ReLU activations function to introduce non-linearity and help the model learn more complex patterns. This layer doesn't need an input shape because TensorFlow infers it from the previous layer's output shape. For this case, and the final layer, the final layer is another dense layer with 10 units, representing 10 possible output classes. We use softmax as the activation function here, which is common for multi-class classification problems. The softmax activation transforms the raw scores from each neurons into probabilities that sum up to 1, making it easier to interpret the output. For example, if this model was used the digit classification, each unit in this layer could represent a probability that the input belongs to one of 10 classes, such as digits 0 through 9, and calculating parameters for outputs layer. The parameters for this layer are 160 calculated as this one, and yes, each of 10 neurons connects to the 15 neurons in previous layer and each has a bias. Summarizing the model, in our case, each layer's names, type and output shape, the number of parameters for each layer. The output also shows as the total number of parameters in model, which is 10,575 in this case, and all of them are trainable. Trainable parameters means these values will be adjusted during training to optimize the model's performance on the task. Consideration and practical use. In real-world application, you might use the kind of model task like image classification or document categorization. The three-layer structure is relatively simple, so it's best suited for straightforward classification problems. You can extend or modify the model by adding layers using different activation functions or even adjusting number of neurons in each layer adapt to complex data. And our 4.5 exercise is softmax placement as described in lecture, and optional softmax lab. Numerical stability is improved in the softmax group with the loss function rather than the output layer during training. This has implication when building the model and using the model. And for building the final dense layer should use a linear activation is efficiently no activation. The model.compile statement will indicate this by including this does not impact the form of target. In the case the target is expect digit 9, 0 to 9, and for using model the outputs are not probabilities. If outputs probabilities are desired, apply a softmax function. And summary of the concept, and we will before the start the exercise 2. And yes, We set these sentences. Summary of concepts. Sequential stacking of densely forms the basic structure of neural networks. Activation functions like relay and softmax play a role in how each leaves process data. Understanding how parameters are calculated and their role in learning helps interpreting models' complexity and functional performance. Thanks for all.